Morning, everybody. We're all doing well. Let's see, I feel like let's see. Let me tilt my screen here. Sorry. My board's in better view. Chat. So I want to grab. Sorry, 1 moment. So make sure I have Sanders stuff up. So it looks like you guys have started talking about, well, continue talking about the definition of the derivative and some derivatives. And it seems like that is probably what we should talk about today. But if you guys have other questions, you should ask them, because I'm happy to talk about whatever you guys want to talk about. Homework number 3, we can go over some problems. Certainly, yeah, let's take a look. 1 second here. Oh, also let me, yeah, sure, let me take a look at it. Let me give you guys the attendance form. I just want to thank everyone. You guys have been doing a great job of everyone has been filling out the attendance form once and only once, which I really appreciate. It makes my job just a little bit easier. So thank you. Keep it up. Let's see. Let me grab this file. Homework number 3. Oh, sure. Okay. So yeah, this is exactly the kind of limit I was actually, so I'm looking at homework problem number 1. I'm gonna do a slightly different one. I'm actually gonna do a couple different ones. This is exactly the kind of thing I was thinking he might ask you guys about. So let's go ahead and talk about this. Yeah, and we'll actually, sorry. We will go in a slightly different direction first, but we will definitely get there, don't worry. This question really starts by asking, or we really kind of look at this question, really looking at something different first. So I'm going to ask, what's the limit as theta goes to 0 of sine of 5 theta over theta? And now here's the thing. Here's the thing we need to keep in mind in general. If we're taking the limit, so here, let me flip my video here. It all looks backwards to me, which I can't stand. Like, my words are wrong, so let's fix this real quick. Sorry. And when I'm in meetings with people, I like to have my video mirrored, so I look like my normal self. But when I'm writing, I don't want my video mirrored, so it looks like what I'm actually writing. So we know this. We know that the limit as some stuff goes to 0 of sine of stuff over the same exact stuff. Right, so like the limit as theta goes to 0 of sine of theta over theta, or the limit as x goes to 0 of sine of x over x. Whatever that thing that's going to 0 is, if it's here and here, that limit is 1. And we did the geometric proof of that a couple classes ago. Now, the thing that's really important here is that this and this have to be exactly the same. If they're not the same, then the limit won't be 1. So what we do, so like in this problem here, right? I've got sine of 5 theta on top and theta on the bottom, and those aren't the same. So, but the good thing is they're both going to 0, right? 5 times 0 is 0, and 0 is 0. So both of the things are going to 0, which is one of the things we need, right? We need both of them to 0. We need them to be the same. So here's how we fix it. There's a couple ways of doing it. The method I kind of like to do that this is my patented method. It's not really patented, but it is my method. Is I'm going to, what I like to call the wish method. So I'm going to rewrite this fraction as 2 fractions. Sine of 5 theta over something that I haven't written in yet, times something over theta. So this is still the same expression, but written differently. And now whatever else I add in, I have to kind of account for. So here's the question. My pens are like, damn, this black dust is killing me. So what do I wish I had beneath sine of 5 theta? What would make my life a lot easier to have right there?
5 theta.
Exactly. And here's the thing. If I divide by 5 theta, I also need to multiply by 5 theta to cancel it out so that I haven't changed anything. Now, I'm not going to cancel them out, but I am going to recognize that this limit and this limit are the same limits. They just look a little different. And now look what happens. I can cancel the theta here and the theta here. And this is just 5. If I wanted to, I could even bring that 5 out in front. I could write this as 5 times the limit as theta goes to 0 of sine of 5 theta over 5 theta. Usually we just skip this step and we say, hey, the limit of this, that's going to be 1. Because I've got the limit as theta goes to 0, the sine of some stuff over the exact same stuff, and both of those stuffs are also going to 0. So this whole thing is 1, so the entire thing is 5 times 1, which is 5. And this kind of idea will always work for something like this. So for example, let's do another example. Let me see. Yeah, and there are other ways to do this, which I will maybe address in the next problem, but that's kind of the basic idea. So let's do another one. Let's do the limit as, and you can use x or theta or t or whatever variable you like. Limit as x goes to 0 of sine of 6x over 8x. And here's the thing, with enough practice, you will get to recognize that this limit is going to be 6/8 or 3/4 after you reduce. If you have sine of a thing over another thing and it's just something times x, you always just get the coefficients, which is nice. But you still should show the work. So I'm going to do this as the limit as x goes to 0 of the sine of 6x over some stuff times something over 8x. And what do I wish was there?
6x.
Thank you. If I have one there, I have to have one there. And then here's what happens. This part just becomes 1 because the limit as x goes to 0 of sine something over the same something as 1. Here the x's cancel and you get 1 times 6/8, which is 3/4. Now it also works for reciprocal type things. So I was going to take the limit, in fact, let's do this one first. Let's do the limit as x goes to 0 of x over sine x. Now here's what we know. We know the limit as x goes to 0 of sine x over x is equal to 1. There's actually kind of an interesting thing that's true in math, which is that if you have a limit of something equal to 1, its reciprocal will also equal 1, or its reciprocal will just equal the reciprocal of it. But we can show it. We can say, hey, look, this is the limit as x goes to 0 of 1 over the flip. Right? Because if 1 divided by a fraction, you would flip and multiply, and that would just be 1 times x over sine x, which is exactly that. But then we have those limit rules. Right? There's a rule that says you have the limit of a fraction, it's the limit of the top divided by the limit of the bottom. So this is really the limit as x goes to 0 of 1 divided by the limit as x goes to 0 of sine of x over x. As long as the bottom limit isn't equal to 0, which it's not. What's the limit of constant? Just the constant. What's the limit as x goes to 0 of sine x over x?
1.
Thank you. Appreciating all the talking. Thank you guys. So yeah, so the thing we actually see is if you have sine x over x or x over sine x, you still get 1 for the limit. And so if I had, for example, I'm not going to do the work for this one, but if I had the limit as x goes to 0 of 3x over sine of 3x, I would know that limit is 1 because I have the same stuff, and it doesn't matter if the sign is on top or on the bottom. If it's the same stuff that's going to 0, sine of that stuff over that stuff, or vice versa, that stuff over sine of that stuff, the limit's going to be 1. Okay, we're getting close to being able to answer the question. There's a couple more things we need to do because it's good practice. I was going to say, if you had a test, I would imagine there would be a question like this on your test. Let's do a couple more. Don't worry, we're working our way to tangent. We're almost there. So limit as x goes to 0 of, say, like, I don't know, 3x over sine of 7x. We could tackle the same way. we could write it as two fractions, 3x over something and something over sine of 7x. And the thing in here is you have to make sure you kind of match the one that's harder to match. You're always trying to match what's in the sine function. So I'm not trying to figure out what goes down here. I'm trying to figure out what goes up here. And what's going to go up there?
7x.
Yeah. And down here, we have to have a 7x to balance that out. And then these cancel. You can pull out the 3 7s in front if you want. You don't really need to. But this is equal to 3 7s times the limit as x goes to 0 of 7x over sine of 7x. And that's just 3 7s times 1. Just to point out, some people do like to do this differently. I'll show you how someone else might do this. So some people do this by saying, I know the answer is going to be 3 7s. So I'm essentially going to factor out a 3 7. So look, I can rewrite this as, I can write 3x as 3 7s times 7x. Right, that's still true. 3 7s times 7x is 3x. And then sine 7x at the bottom. And then you can just pull this out in front. But if you're like doing it this way, you really have to kind of know what the limit is supposed to be before you start doing any work. Whereas this way, you can just kind of break it up into pieces and be like, oh yeah, I know what needs to go with sine of whatever, the whatever. So I would do it this way, but you could also do it this way. Either way is fine. All right, yeah. Moving on to tangent. So the thing about tangent is it works just like sine as far as these limits are concerned, because tangent is sine over cosine. So if I was trying to find the limit as x approaches 0, let's use theta. Let's try to use, it's good to be comfortable using theta or x or anything. Say tangent, let's just do tangent of theta over theta. Here's the thing. I can rewrite this limit as theta goes to 0. Well, tangent of theta is sine of theta over cosine of theta, all over theta. I probably wouldn't actually write it like that. I'd probably actually write it as sine of theta over cosine of theta. And if I'm dividing by theta, I'm really multiplying by what? Let me say it this way. Dividing by 2 is like multiplying by 1/2.
1 over theta.
Exactly. Yeah. Yeah. Someone just asked for the. Yeah. Of course. I'm always happy to provide the attendance link. And again, you guys can totally just bookmark it if you want on your computer, so because it's just the same link every time as I think it is. So you should still only fill it out when you come to class, but definitely, bookmark it if you want to. That way it's easier. And then I'm going to rewrite this fraction, right? Because when you write, this is really sine theta times 1 over cosine theta times theta. But I could regroup things so it's sine theta over theta times 1 over cosine theta. It's perfectly legit, right? The top is still sine, right? Because sine times 1 is sine. The bottom is still theta times cosine theta. I've just written it in a different order. And now I would just say this is going to be 1 times 1 over cosine of 0, but I could do one more step to be a little bit more precise. So what we're really doing here is we're using one of those other limit rules. This is the limit of a product. I can write as a product of 2 different limits. I can write it as the limit of sine theta over theta times the limit of 1 over cosine theta. That's allowed as long as both limits exist. So if you do this and then you get something where like you get like division by 0 or something weird, you can't actually do it. Here's the attendance link again. So we know this limit. We've seen it a bunch of times by now. It's 1. And this limit we can just do by plugging in. If I plug in 0, I get 1 over cosine of 0. What's cosine of 0? It's not 0. So I get 1 times 1 over 1, which is 1. So here's the deal. Just like the limit as theta goes to 0 of sine theta over theta is equal to 1, the limit as theta goes to 0 of tangent theta over theta equals 1. So we can now say, well, so he might want you to show more work for the one he's actually on the homework. I don't know. But if I was doing the limit as theta goes to 0, say like tangent of 4 theta over theta, I might do 2 different things. So if I was doing less work, I might just do this. I might do the limit as theta goes to 0. Say, okay, I want tangent of 4 theta over something, and then something over. Yeah, let's make it more fun. Let's make it a 6 theta. And so of course, what do I want down there? Somebody.
4 theta.
Yeah. And then if we have 1 there, we have to have 1 there. And then since I know the limit as theta goes to 0 of tangent of a thing over the same thing, as long as both the things are going to 0, that's going to be 1. So then I end up with just 1 times 4/6, which is 2/3. But that might not be enough work to show. He might really want you to do this instead. So I'm going to do this again on the other side. Ooh, it's getting warm in here. Definitely gonna it's gonna get real hot in this room as we get more summery. Well, not that it's summer yet, obviously, but if I do the same limit here, tan 4 theta over 6 theta. I said tan. I never say tan. I say tangent. Not that, but I mean, I was gonna say not that it's wrong to say tan, but it's kind of wrong to say tan. You should say tangent. It's a better thing to say. Okay. So what I imagine he might want you to do for something like this is actually to break up the tangent, sine, and cosine. So I would write this as the limit as theta goes to 0 of sine of 4 theta over cosine of 4 theta times 1 over 6 theta. So it's a 6 theta, not a 60. Apologies. And then I would break it up so that I can have the sine by itself. The limit as theta goes to 0. Sine of 4 theta over something times something over 6 theta times something over cosine 4 theta. I might just put a 1 up there, right? If I don't have anything I need to put there, I'll just put a 1. What do I need down below sine of 4 theta? 4 theta. And then I need to balance that out. But then my thing is totally balanced and this is going to be fine. So I just put a 1 over there. And then this part goes to 1. These thetas cancel and you get 4/6. And 1 over cosine of, let's see if I plug in 0, cosine of 0, you get 1 times 4/6 times 1 over cosine of 0 is 1. So I get 4/6. And that's how I kind of imagine he probably wants you to do something similar to problem 1. So I'm not going to do problem 1 exactly, but let's do one that's very similar. Let's say the limit, let's say they go, I feel like this one's, we'll do one more and then we'll move on. Let's do tangent theta over 7 theta. So I want you guys to break this up. Well, in fact, so let's do the first part together. I'm going to write tangent theta as sine theta over cosine theta. And instead of writing all of that divided by 7 theta, I'm just going to write times 1 over 7 theta. All right, so now I want you to rewrite it so that you have sine of theta over what you want to have it over. And I'll give you a minute. Literally 1 minute. All right, it's been a minute. So I know I have all this. So I have a sine theta, and I have a cosine theta in the bottom, and I have a 7 theta in the bottom. And what do I need beneath sine of just theta? Just theta. If I put a theta in the bottom, I need a theta in the top to cancel it out, or to balance it out, I should say. Now I don't really want to put it here, because theta over cosine theta doesn't help me. I want to put it here. I mean, you could put it there and cancel it there still. But I want to put it here so I can see that it cancels out with that theta down there. And then I want one there. Alternatively, if you wanted, you could just have been like, oh, this theta I'm just going to put underneath sine. It's the same work. It's just a kind of different way of imagining it. So we end up with the limit of this part is 1. 1 over cosine of 0 is 1. And the theta is canceled, I'm left with 1/7. So I have 1 times 1/7, which is 1/7. That's how that works. So problem 1 is very, very similar to that. I think you can handle it now. Let's see. Almost anything else there? No. Cool. Good stuff. So let's see. What other homework? I mean, we can look at all the homework problems, but if there's anything specific ones you guys want me to address, I'm happy to take requests. Again, I'm not going to do exactly the homework problem, but I can definitely do similar-ish problems. Black ghost. Similar number 6, sure. Okay, yeah. So the secant line for cool. Let's see. Do I want to use that same function? I'll make it a little bit different. Okay, so compute the secant line. For what do we got here? And clearly it's the same function that's in function 5. So for, let's say, f of x equal to, what do I want to use here? Do I want to use a square root? Not really. Sorry, one sec. Let me think. We're going to take the derivative. Or we're not going to take the derivative. Okay. Let's do this. Let's do. I'm not trying to be too complicated here. Let's do the cube root of what? Sorry. X minus 4 on the interval from what? 5 seems lame. Let's go on the interval from 12 to 31. Okay. Similar-ish question. Yeah. So what we're trying to calculate here is the line, right? So when they say compute the secant line, what they're really saying is, okay, find the y equals mx plus b. Or if you prefer the point slope form, y minus y1 equals m times x minus x1. So that's our job to do. And so our function looks kind of like this. I'm not going to do a great job of drawing it here, but it kind of does this deal. Right, it doesn't have to be super precise. And let's say here's the point 12 comma. So if I plug in 12, well, the y value is going to be, let's see, f of 12 is the cube root of 12 minus 4, which is the cube root of 8, which is 2. And similarly, this other point over here, where we have 31, this is the point of 31 comma f of 31, which is, if I did things right, the cube root of 31 minus 4, which is the cube root of 27, which is 3. Okay. So great. Now that we have 2 points, we can find the equation of the line that connects them. So here's the thing, that the language you need to know here is that when someone says the secant line, they mean the line that goes through these 2 points on this graph. So I'm just trying to find the equation of that line, which is supposed to be a straight line, but doesn't look that straight. Well, great. To find the equation of the line, we need two things. We need a point. Well, great. We've got 2 different points. That's no problem. And we need a slope. So point, we're good to go. We've got the point. You can use either one. 12.2 or 31.3. Slope, well, if we have 2 points, we can find the slope between those 2 points. The slope is just the difference in the y's over the difference in the x's. So the change in y over the change in x. Or you can write it as y2 minus y1 over x2 minus x1. So the difference in the y's, that's going to be, so it doesn't matter which order you subtract as long as you're consistent. It can either be 3 minus 2 over 31 minus 12, or it can be 2 minus 3 over 12 minus 31. Either way, perfectly fine. This way I get 1 over, let's see, 31 minus 12 is 19. This way I get negative 1 over negative 19, which is the same thing. Great. I've got a point. I've got a slope. Let's see, I don't want to erase too much here. I think there's another one in the direction. So then, if I've got a point and I've got a slope, I can write the equation of the line like 3 different ways. I could write it as y minus this y value equal to my slope times x minus the corresponding x value. That would be perfectly fine. I'm a fan of leaving it like that if they don't tell me I have to do something different. He didn't say you had to write it in the y equals mx plus b form, so you could just leave it like this. But you could also change it to y equals mx plus b. Let's say this is y minus 2 equals 1/19 x minus 1/19 times 12 is 12/19. Then you can add 2 to both sides. You get 1/19 x minus 12/19 plus 2, but 2 is 38/19. And I just multiplied 2 over 1 by 19 over 19. And then I get 1/19 x, negative 12 plus 38 is 26/19. So you can also do that. Either of these are acceptable in my book, but if you had to kind of, if you had to guess which way someone wanted you to do it, the safer guess is to probably write it like this. And yes, exactly, Genevieve, the slope does come from the average rate of change. So the slope of the secant line between 2 points is exactly the average rate of change between those 2 points. Because if we look at this, essentially we're going over 19 and we're going up 1. So right, the average rate of change is up 1 for every 19 we go over. Now, obviously that's not the rate of change everywhere, right? The rate of change here is a little bit steeper. The rate of change here is a little bit less steep. I should say the instantaneous rate of change there, the slope of the tangent line, is higher, steeper, and the instantaneous rate of change here, which is the slope of the tangent line, is less. That's fine. This is just the average rate of change over that interval. So what I was going to say, but I think you guys kind of beat me to the punch, is that if you were doing problem 5, or if you did problem 5 first, the answer you got to problem 5, the average rate of change, would just be your slope in problem 6. So if I had done problem 5 first, if I had said, what's the average rate of change of this function over this interval, I would have gotten 1/19. And then I would have used that as my slope in problem 6. Are there other questions about this? Are there other questions about other things? Yeah, good. I was hoping someone would get there. So limit definition of a derivative. Now, here's the thing about this. Limit definition of a derivative, there's 2 different versions of it. There's limit definition of a derivative at a point, which is what all these are asking about. And there's also just the limit definition of the derivative as a function. And I'm going to kind of show you both right now because most people spend like this much time on derivative of a point and then this much time on derivative as a function because that's kind of important. But let me look at a different problem. So we'll get around to something like that one. That one's a little bit of a pain in the butt, I'm not going to lie. But let's look at something slightly different and we'll kind of see. Yeah, so let's use the limit definition of the derivative to find, let's see what I want here. The derivative of f of x equal to x squared plus 3x at the point. He just gives you at x equals 1. So you could say at the point 1 comma 4, or you could just say or at x equal to 1. It's the same information, essentially. Okay, so I'm going to show you two ways of doing this. The first way is probably the way he kind of means to do it. Yeah. So you get the average rate of change. That's exactly what I did, Genevieve. Right? If you look back here, that's exactly what I'm doing. I'm doing 3 minus 2, which is my f of, right? So if you're calling, let me just do it right here. If you're calling this a and this b, right? Then I'm doing f of b minus f of a all over b minus a to get the slope of, or sorry, to get the average rate of change. And again, really, just the average rate of change is exactly the same thing as the slope of the line between 2 points. Okay, so method 1. Sure. So what I want you to notice that the limit, how do I write this? Okay. So f prime of 1 is equal to the limit as, I wonder how he's doing this. Here's how I'm going to do it. Limit as h goes to 0 of f of 1 plus h minus f of 1 all over h. So that's how we find the derivative of a function at a particular point. More generally, right, if your point is a, so generally, if x equals a, we say that f prime of a is the limit as h goes to 0 of f of a plus h minus f of a over h. I don't remember if he used these letters exactly because I was zooming through his lecture, so I didn't catch if he was using a's or h's, but it's the same idea that my word is using. So I'm just going to calculate this. Now here's the thing to remember for any of these limit definitions of the derivative. You have 2 goals. I mean, you have one goal, but you have an intermediate goal before that. Your ultimate goal is to make this first h in the denominator cancel out. That is our goal, always. The intermediate goal we need to get to before that is to make sure all the things in the numerator that don't have h's cancel out. Because if all the things that don't have an h cancel, then everything else will be left with an h, and you can factor that h out and cancel it with the h on the bottom that we're trying to cancel out. So that's our goal, is to cancel that h out. So I'm just going to plug in my 1 plus h and my 1 to my function. So I'm still going to write the limit. And then I'm going to say, okay, well, let's see. F of 1 plus h. I know that f of x is x squared plus 3x. So f of some stuff is my stuff squared plus 3 times my stuff. And the stuff is 1 plus h. Minus f of 1, which is my stuff squared plus 3 times my stuff. My stuff here is 1. Okay, now I'm making an error here that I'm going to correct, but I want you guys to see something. So don't write this down just yet, or be prepared to fix it if you do write it down. It's not a huge fix, but here's what's going to happen. So if the limit as h goes to 0 I'm going to multiply this out. So 1 plus h squared is 1 squared plus 2h plus h squared. 3 times 1 plus h is 3 plus 3h minus 1 minus, sorry, plus 3. I'm sorry, I'm trying to correct the mistake I know I'm making. And here's the thing that I'm seeing. 1 squared is just 1. I probably should have written 1. The 1 and the negative 1 cancel out. The 3 and the positive 3 do not cancel out, and that's an issue, right? All the not h things should cancel out. And the reason they're not is because I made a mistake. The mistake I made was that I forgot that it was minus all of this, meaning this minus sign should distribute across the 1 plus 3. So really you could just add 1 and 3 together to get 4 and take minus 4. So really that's what I should have here. It's minus 4 or minus 1 minus 3, either way you want to write it. But what should happen is the not h things, so 1 plus 3 minus 4, those all add up to 0, so they cancel out. So if you're not getting the not h things canceling, go back and make sure you distribute it correctly, because that's usually where the error is happening. Okay. Then everything else has an h. I've got a 2h, I've got an h squared, and I've got a 3h. Okay, I'm like, why does this seem weird? Yeah, okay, it's fine. Yeah. So I'm going to factor out an h. I might even add, I don't know, you can do whatever work you want. I'm going to factor out an h and get 2 plus h plus 3. What I was going to say is you could have added the 2h and the 3h together first and get 5h, but it's not really necessary. These h's cancel, and then after you cancel that h in the denominator, you can let the rest of the h's go, or you can plug in 0 for the rest of the h's. So I get 2 plus 0 plus 3, which is 5. That's a perfectly fine way of doing a problem like this. The issue is I'm spraying water everywhere. Sorry, 1 second. Jeez. What happens when you don't finish drinking your water before you take the straw out of your mouth? Okay, sorry about that. Yeah. The issue here is that this is fine, but then what if I asked you to find the derivative at 2? And if I was going to find the derivative at 2, I have to go through all this work again. And then what if I asked for the derivative at 3? So the thing is, there's a better way to do this so we don't have to repeat this work every time we want the derivative of a new point. And that's take the derivative as a function of x and then plug in whatever value x you want. So I'm going to show you this one again, and then we'll definitely look at something more similar to number 9 or 10, and then we'll look at something like 3 or 4. Okay, I'll try and be quick though. Yeah, sorry, I gotta move a little bit faster. Apologies. So I'm wondering, I'm trying to think, like, should I do this way? So here's what I want to say. My function was this. F of x equal to x squared plus 3x. And instead of finding f prime of 1, I can find f prime of x, like the derivative as a function, which is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. Same idea, except instead of using, right, instead of finding the derivative of 1, we're doing f prime of 1 equals f of 1 plus h minus f of 1 over h. Now I'm replacing whatever number it is with the variable x. Right? X, x, x. Then the work is going to be very similar. I'm going to try and do it kind of quick here. Make the limit as h goes to 0. F of x plus h, so instead of x squared plus 3x, it's going to be my stuff squared plus 3 times my stuff. My stuff is x plus h. Minus, that's the crookedest line I've drawn in a while. F of x, which is x squared plus 3x. Remember, it's minus all of it. All over h. We're going to multiply this out. You should get very good at multiplying out x plus h squared, because it's going to come up relatively frequently. 4 prime marks mean the same thing as 1. Sorry, you guys are asking some questions. Oh, when does it? So you can use a prime mark, but if you want to take higher derivatives, so like if I want to take the second derivative, you would write it as f double prime of x. The third derivative would be f triple prime of x. But then the fourth derivative and higher derivatives, you write using what he said is superscript with a parentheses like that. So that notation means the fourth derivative of x of f of x. And this notation of the 5 would mean the fifth derivative of the function f. So hopefully that clarifies that. So this one, we multiply this out, you get x squared plus 2xh plus h squared plus 3x plus 3h minus x squared minus 3x divided by h. Cancel the non-h things, x squared and minus x squared, 3x and minus 3x. The rest of the things have an h. So instead of factoring out h, I'm just going to divide each thing by h, which is the same thing, really. Take the limit as h goes to 0 of 2xh divided by h is 2x. H squared divided by h is just h. And 3h divided by h is 3. And then letting the rest of the h's go to 0, I end up with just 2x plus 3. So the derivative of x squared plus 3x as a function is 2x plus 3. And then I could say, okay, this is my f prime of x. And then I could find the derivative at any point I wanted. I can say, oh, well then f prime of 1 is just 2 times 1 plus 3, which is 5, just like we got on the other side. So you can do these problems. You probably are meant to do these problems the first way, where you're just doing the derivative at a particular point. But you should be aware there is this other way that we're going to start doing derivatives where you actually just do it at x and then you can plug in whatever value you want. Now, let me take a look here. Yeah, good time. Okay. So 1 over x squared is kind of a bigger pain because it's just less nice. Actually, it's not so bad, actually. So let me do one very similar to that, and then I can definitely look at something like 3 or 4. I will say for problem 4, the idea there is that, actually, let me address problem 4 real quick, just because I know I can do it real quick. So the function, I'm going to make it slightly different. F of x is sine, let's say it's sine of 6x over x. You can graph this on the graphing calculator or on Desmos, and it's going to look like, vaguely like this, where it's undefined right there when x is 0, and this point is 0 comma something. And we essentially, right, it's undefined there. There's a hole there at 0 comma something. And what he's really asking you to say is, what should the value there be, right? He's asking a question for, choose a value for f of 0. So what does f of 0 need to be? Well, it needs to be whatever this function is approaching as x is approaching 0. So in other words, what's he really asking you to find? Starts with an L, ends with an imit. Okay, my jokes aren't funny, it's all right. He's asking me to find this limit. We know how to find that limit. We spent the first 20 minutes of class today doing those types of limits. What's that limit going to equal? I would say show me on your fingers, but no one's got their videos on. Or at least I don't see the videos. Yeah, limit 6, right? And you would show that by doing it the way we did, but I don't want to spend time doing that. So that means we want f of 0 to equal 6, right? That's what would make this function work out. So that's how you answer number 4. I mean, it's not exactly that, but it's very, very similar to that. So I'm going to ask the question. Sure. So I want to find f prime of 1. 1 is less exciting. For f of x equal to 6 over x squared plus 1. I'm going to make it a little bit more interesting. The process is still going to be the same. So just like we did on the first one, we did like this, right? F prime of 1 is the limit as h goes to 0 of f of 1 plus h minus f of 1 all over h. So what you always want to start with, right? If you're asked to do a limit definition of a derivative, you always have to go back to this limit as h goes to 0 of f. Okay, so f of 1 plus h, I'm just going to plug in 1 plus h for x, right? So I plug in 1 plus h there, I get the Make sure you write the limit until you actually find it. You get 6 over x plus, sorry, not x, 1 plus h squared plus 1 minus f of 1, which is 6 over 2, just 3, all over h. And now for this one, you have to do something where you get those, put those fractions together. Now let's simplify a little bit. Simple limit, h goes to 0, 6 over 1 plus h squared, I'm going to write out as, I'm going to think of it as h plus 1 squared. It's h squared plus 2h plus 1, and then there's another plus 1, so it's actually plus 2. Minus 3 all over h. I need a common denominator in the top. So what I'm going to do is I'm going to multiply that 3. I'm going to multiply this by h squared plus 2h plus 2 over the same thing. So I end up with the limit as h goes to 0 of 6 over h squared plus 2h plus 2 minus 3 times h squared plus 2h plus 2 over the same thing. All over h. Now, instead of dividing everything by h, which looks kind of messy, I'm going to say instead all times 1 over h. That's a very, very common thing people do to make it just look less terrible. So now we're going to simplify. And again, what should happen here is in this fraction, the things on top that don't have h's should cancel out, which looks like it will, because I mean I have a minus 3 times 2, which would be minus 6. So here's what I get. Limit h goes to 0 of, well, it's one fraction with a common denominator. And then I've got 6. Minus distributes to each term, or I should say it's a minus 3 distributing each term, so it's a minus 3h squared. Minus 3 times 2h is a minus 6h. Minus 3 times 2 is minus 6. All times 1 over h. The 6 and the minus 6 cancel. Let's factor out the h from the top and see what happens. Limit h goes to 0. Factoring out the h, I'm left with a negative 3h minus 6. All over h squared plus 2h plus 2 times 1 over h. And this 1 over h cancels out with this h right there. Right, and again, we're always trying to make this h in the denominator cancel out. And then the rest of the h's, how do I get negative 6 over 2? Because I plugged in f of 1. Right? F of 1 was 6 over 1 squared plus 1. Make sense? Also, just in general, if I'm not answering your question that you've chatted, it's because I haven't seen it. So you can always say things, and I will try to get to it. And now that we've canceled out this h that would make us divide by 0 if we plugged in 0, the rest is good. I plug in 0 for all the other h's. This goes away. This goes away. This goes away. And I'm left with negative 6 over positive 2, which is negative 3. So the problem 9 that he asked would be done in a very similar way. And it would look kind of gross because you would have, 1 over 1 plus h squared. You have to multiply it out and then do the common denominator kind of thing that we did here. So it's a very similar process. We've got a minute left. I think I can definitely say something useful about problem 3, and then we'll call it a day. We'll call it a week. What is it, week 4? Week 400? Not bad. Okay, so looking at, and I don't have the brain power to make something up right this minute, so I'll just do this one. I'll make it slightly different. X is less than or equal to 1, and x squared, 2x squared plus 1, when x is bigger than or equal to 1. That's not going to be exciting. Let's make it plus 4. Okay, so here's the idea. The question is, choose a value of a that will make the function continuous at 1. And what's happening is, right, this function is some line, right? You've got ax plus 3. So, maybe it looks like this, where, right, this point is 0, 3. the slope is a, and then here you got some parabola that's doing, I don't know, something like that. So the thing is you want this value here and this value here to actually meet up. So the easy way, the kind of less mathy way of doing it is just to plug in 1 here and 1 here and set them equal to each other. Right? If I set x equal to 1 here, I get a plus 3. If I set x equal to 1 here, I get 2 plus 4. A plus 3 equals 6. A equals 6 minus 3 is 3. So A would have to be 3 in this particular example. Now, the work that's really happening here is we're saying, well, if we want this to be continuous, we have to meet the definition of continuity. Specifically, the limit has to exist as x approaches 1. So the limit as x approaches 1 from the right, which uses this piece of the function, I can just plug it in and get 6, right? Because 2 times 1 squared plus 4 is 6. The limit as x approaches 1 from the left is a times x plus 3. Or sorry, I'm using the function a times x plus 3. And then I'm plugging in 1 for x, and I'm getting a times 1 plus 3. But the limit from the right and the limit from the left have to equal each other. So that's actually where I'm getting that a plus 3 has to equal 6, because the left-hand limit and the right-hand limit have to be the same. So he probably wants you to show work like this for that problem. So for problem 3, I would definitely do the left-hand limit of your ax, whatever, do the right-hand limit of your function, get some number, and then after you've done those limits, say, oh, those limits have to equal each other because of continuity, right? For the function to be continuous, you have to have a limit existing everywhere. And so then you can say, oh, that equals that, and then I can solve for a. A plus 3 equals 6, so a equals 3. That's how you would do a problem like problem 3. All right, good questions, you guys. I will see you all on Monday, and I'll try and get a quiz posted up sometime soon, today or tomorrow. We'll see. All right, take care. I'll get this video posted to Canvas soon. Oh, and make sure you fill out the attendance form if you didn't already, but only if you didn't already. All right.